The moon hangs above the sleeping side of Earth with a face so familiar that it can almost disappear into habit. A pale disk, a quiet companion, a shape known before language, before maps, before any machine ever left the ground. Yet under that soft light, its surface is not smooth, not simple, and not still. It is a cold archive of scars, frozen waves, broken mountains, buried ice, and old fire. Before drifting closer to that world, take a moment to settle in. If this kind of slow journey through space helps you rest, study, or simply let the noise of the day fade a little, consider subscribing, leaving a like, or sharing the video with someone who enjoys the quiet side of astronomy. And if you feel like it, write in the comments where you are listening from and what time it is there. While the moon rises or sets somewhere beyond your window, you can turn the lights down now, lower the screen brightness, let the room become softer, and find whatever position feels easiest. Maybe there is a fan moving gently nearby. Maybe the night outside is completely still. Either way, there is no need to hold on to every detail. The moon has kept its records for billions of years. It can be listened to slowly. For a long time, it seemed like a dead grey stone circling Earth. But the closer the cameras came, the less dead it appeared. Across its surface are craters inside craters, slopes that have quietly collapsed, valleys cut by vanished lava, and polar shadows that may never have seen sunrise. The journey begins with the nearest world in space, and, with the strange marks written across its silent ground, the moon is the easiest world in space to forget. It is there on so many nights, crossing above rooftops, fields, oceans, and quiet roads, that its presence becomes part of the background of being alive on Earth. It fades behind clouds. It appears over cities where no stars can be seen, and still its face remains clear enough for the eye to recognize. Dark plains lie across it like old stains. Bright highlands catch the sunlight. That familiarity is deceptive. The moon is close enough to seem known, but distance is not the same as understanding. For most of human history, it was a light in the sky, a calendar, a symbol, a clock for tides and seasons. Its changing shape helped people measure time, plant crops, hold ceremonies, and imagine stories about the night. Long before spacecraft, the moon already belonged to human memory. But the actual world beneath that light is stranger than memory allows. It has no air to soften its outlines. No weather crosses its plains in the earthly sense. No rain falls there. No river bends through a valley. No wind moves dust across the open ground. Once a footprint is pressed into the fine powder of its surface, nothing like ordinary weather arrives to erase it. Change still happens, but it happens in another rhythm, under a sky that is always black, beneath sunlight that is harsh and unfiltered, over spans of time so long that erosion becomes almost a form of silence. The surface is not empty. It is crowded with evidence. Every crater is a record of a collision. Every slope carries the memory of falling rock. Every smooth plain once belonged to molten material, spreading out over lower ground before cooling into dark basalt. Every bright ray is a spray of crushed stone thrown across the surface by an impact sudden enough to melt rock and raise mountains in the center of a hole. The moon does not speak, but its ground is marked almost everywhere. It has been written on by the early solar system, by wandering fragments of stone, by heat from within, by gravity from Earth, and by sunlight that arrives without atmosphere to filter it. Seen from Earth, all of this is compressed into a disk. The eye cannot easily sense depth. A mountain becomes a small bright edge. A basin becomes a grey patch. A crater wall becomes a ring, and the shadows inside it seem still and simple. Through a telescope, the surface becomes more complex. The Terminator, the line between lunar day and lunar night, cuts across the moon and turns low relief into long black shape. Ridges appear, floors sink, peaks rise inside craters like islands caught in light. For a few hours, the familiar disk becomes a landscape. Then spacecraft change the scale again. The Lunar Reconnaissance Orbiter circles the moon with a camera sharp enough to see details that no backyard telescope can hold. Since 2009, it has passed over the highlands, the Maria, the far side, the poles, and the scarred rims of countless impact sites, gathering images under many angles of light. It does not see the moon as a symbol. It sees it as terrain. It sees walls, boulders, cracks, pits, ridges, flow lines, shadowed floors, and slopes that carry fresh trails where material has moved. That matters because the moon can look dead from far away. Its face does not change from week to week in the way a cloud deck or an ocean changes. There are no blue storms forming across it, no white caps of weather, no green belts of life. The same large, dark plains remain visible generation after generation. A person looking up now sees nearly the same broad pattern seen by ancient observers, yet stillness at that distance hides motion at another scale. Tiny impacts strike the ground. Dust is thrown and settled. Heat expands the surface during the long lunar day and lets it contract again during the long lunar night. Slopes fail. Boulders roll. New craters appear, small but real. The moon is not active in the same way Earth is active, but it is not finished. It is cooling. It is flexing. It is being struck. Slowly darkened. Slowly brightened in places, and slowly read by machines above it. The contrast with Earth makes the reading possible. On Earth, the oldest scars are often swallowed. Rain wears them down, rivers cut through them, plants cover them, plates shift, continents break, oceans open, and the crust itself is recycled into the deep interior. Earth is alive with processes that destroy old evidence while making new ground. The moon keeps evidence differently. With no thick atmosphere and no liquid water moving across the surface, marks can survive for astonishing lengths of time. A crater formed billions of years ago can still hold its circular outline. A lava plain can still lie dark and smooth. A wrinkle in the crust can remain visible long after the force that made it has faded. This is why the moon is more than a nearby object. It is a preserved surface from a violent age. Its rocks carry pieces of the story of Earth too, because both worlds formed in the same young solar system, under the same bombardment of leftover debris. The moon records impacts that Earth also suffered, but Earth has buried most of its old wounds. The companion in the sky kept many of its own. There is something quiet about that. A world so close that it lights bedrooms and sea cliffs, yet so ancient in its surface that it holds memories older than almost every landscape on Earth. A world that looks soft from below, though its ground is made of broken glassy dust, jagged rock, and frozen shadows. A world that follows Earth faithfully, while keeping one hemisphere turned away, preserving a far side that no human eye saw until spacecraft first curved around it. The journey across it begins not with the largest basin or the brightest crater, but with a smaller kind of puzzle. On the moon, even an ordinary hole in the ground can contain a second shape inside itself, and then another. Some craters look as if the surface has been struck, lifted, and rearranged from below after the violence has passed. Their rings do not behave like simple impact scars. They resemble frozen ripples in stone. The familiar moon is already becoming less familiar. Its face, seen from Earth as a single calm disk, begins to open into layers. A crater seems, at first, like one of the simplest shapes a world can make. Something falls from space. It strikes the ground with enough speed to crush stone, throw dust outward, and leave a bowl behind. The shape is round because the energy spreads away from the impact point in all directions, even when the incoming object is not perfectly vertical. On the Moon, that simple mark is everywhere. Small craters sit on the floors of larger ones. Larger craters overlap still older basins. Some have bright rims and sharp walls, because they are young enough that space has not yet softened their edges. Others are muted and low, their outlines worn down by later impacts and by the long work of micrometeorites breaking the surface grain by grain. The whole Moon is layered this way, not with soil and rain and roots, but with collisions. But some craters do not behave like ordinary bowls. Belle E is one of those places. It is not famous in the way the great lunar basins are famous. Yet seen from orbit, its shape raises a quiet problem. The crater does not simply fall inward from rim to floor. It carries a second ring inside itself, a raised inner structure that makes the formation look like a circle nested within a circle. It has the appearance of a frozen ripple or a depression that tried to heal from below and stopped before the motion was complete. These are called concentric craters, sometimes donut craters, because the eye sees that inner ring immediately. The first explanation seems easy. Perhaps two impactors arrived in nearly the same place. Perhaps one object struck first, and another followed later, close enough to leave a second bowl inside the first. The Moon has been hit so many times that coincidence cannot be dismissed completely. There are places where overlapping impacts really do make strange patterns by chance. The difficulty comes from the way these concentric craters are distributed. If they were mostly random double impacts, they should be scattered across the Moon in a more random way. They should appear wherever luck placed one strike near another. Instead, many are grouped around certain lunar regions, especially near the edge of Oceanus Procellarum, the great dark expanse on the near side. That clustering changes the meaning of the shape. It suggests that the ground itself mattered. The age of the craters matters too. Many seem to belong to similar broad periods in lunar history. Their floors are also shallower than expected when compared with ordinary craters of similar size. A fresh crater of a given width should usually have a certain depth, because impact excavates material in a predictable way. Belle E and others like it do not quite follow that rule. Their floors appear lifted, as if something came upward after the initial wound was made. The Moon once had more heat inside it than it does now. Early in its history, parts of the interior remained warm enough to melt rock. Basaltic lava spread across low basins, filling them with dark plains that are still visible from Earth as the Lunar Maria. Those plains look like seas only from a distance. They are stone now, but they began as fire. Around those ancient volcanic regions, the crust may not always have behaved like a cold, solid shell. There may have been places where material below the surface stayed warm, mobile, and pressurized. Not liquid enough to pour freely across the surface, perhaps, but soft enough that an impact could disturb it. In one possibility, the ground at the time of impact had a consistency somewhere between rigid rock and melt, not like water, but like cooling lava that still remembers motion. The strike would send waves through it. Those waves would travel outward, slow down, and freeze before they flattened. A circular ridge could remain as the surface cooled. There is another explanation that fits many cases better. After the crater formed, magma below the floor may have pressed upward. It did not always break through as a visible eruption. It may have risen beneath the crater like a slow breath under a blanket of stone, lifting the center and changing the shape of the floor from below. The outer rim remained the scar of impact, while the inner ring became a sign of pressure beneath the wound. In that reading, a concentric crater is not one event, it is at least two. First comes the strike from space. Later comes the response from the Moon itself. That second part is easy to miss because the modern Moon looks so still. Its surface now gives the impression of an object whose story ended long ago. But Bell E suggests something more subtle. The impact was not simply preserved, it was modified. The ground did not behave like a passive target. It held heat, it moved. It pushed back in slow geological language. This is one reason lunar craters cannot all be read in the same way. A crater is not only the object that made it, it is also the place where it formed. A strike into cold highland crust leaves one kind of record. A strike near a warm volcanic province can leave another. The same energy, falling from space, may produce different shapes depending on what lies underneath. Concentric craters are small compared with the Great Basins, but their value lies in that difference. They reveal hidden structure without needing a deep drill or a broken cliff. The shape itself becomes a clue. A shallow floor points toward uplift. A clustered population points toward regional heat. A ring inside a ring points toward motion after impact. The old surface stops being a flat record of falling stones and becomes a record of interaction between the outside and the interior. In a sleep-dark room on Earth, the moon may look smooth and silver. From orbit, its ground is full of these quiet complications. Some scars were made in an instant and then left alone. Others were made quickly and then changed slowly, lifted by forces below, softened by later impacts, or hidden under flows of lava. Bell E belongs to the stranger class, where the clean geometry of impact becomes mixed with the memory of lunar heat. The first lesson is gentle but important. The moon was never just a target. It was a world with an inside. Even when its surface seemed silent, something beneath it could still shape the marks left from above. The moon has no rain, but its slopes still fall. Along the wall of Kepler crater, the ground carries long dark trails that seem, at first, almost too delicate for such an old and airless place. They lie against the inner wall like stains poured down a bowl, narrow at the top, wider below, following gravity toward the crater floor. Nothing about them suggests wind, nothing suggests water. There is no stream bed, no softened bank, no weathered channel cut by seasons. Yet material has clearly moved. Kepler is a young crater by lunar standards, sharp enough that its form still feels fresh compared with older, lower, more rounded scars. Its rim rises above the surrounding plain, and its inner walls descend in steep slopes broken by terraces and loose debris. When sunlight comes across the crater at a low angle, the shape becomes easier to read. The wall is not a smooth curve. It is a place of ledges, small canyons, broken shelves, and fine dust, resting at angles that cannot last forever. On Earth, a landslide is usually imagined with sound. Rock cracks, soil tears, trees fall. A hillside moves with a roar, dragging air and water and living things with it. On the moon, the same word becomes quieter. There is no atmosphere to carry noise across the slope. No dust cloud billows in the way it would under a blue sky. Grains rise and fall in vacuum. Stones bounce in long, slow arcs. The event may be sudden, but it leaves behind silence. The dark streaks inside Kepler appear to begin near box-like openings, high on the crater wall. From those small source areas, fine material has slipped downward, spreading into fans and ribbons. The grains are too small for the camera to resolve one by one, which means much of the moving material is likely less than a meter across, and perhaps far smaller. Boulders are visible elsewhere, especially near the bottom, where larger pieces have rolled or tumbled until the slope finally gave them a place to stop. The pattern does not look like one single collapse. It looks layered. Several trails lie close to each other, crossing, separating, and gathering again. Some are darker than others. Some are thin and clean, while others spread more broadly over older material. The crater wall seems to have failed in pieces, not once, but many times. each small slide adding another line to the same slope. That detail changes the moon again. It is not only a museum of ancient impacts, it also has small, recent movements. They do not reshape continents. They do not open oceans or build mountains in the living geological style of Earth, but they are real. A tiny meteorite striking high on a crater wall can loosen dust and rubble. Thermal stress can crack rock as the surface heats during the long lunar day and cools through the equally long lunar night. Gravity, weak though it is, still pulls downhill. Eventually, a surface that seemed fixed gives way. The process is slow when seen across human time, but relentless when seen across lunar time. Every fresh crater begins with sharp edges. Its walls are steep. Its rim is bright. Its ejecta lies across the surface in patterns that still point back toward the impact. Then the small work begins. Micrometeorites pepper the exposed rock. Dust is overturned grain by grain. Slopes shed material. Corners soften. Blocks roll down into lower ground. Over many millions of years, the crisp wound becomes rounded. This is one reason old lunar craters look tired. They have not been washed down by rain. They have not been covered by forests. Instead, they have been sanded by space itself, struck by particles too small to notice individually, and nudged by rare but repeated collapses. The moon's weather is made of impacts, radiation, temperature, and time. There is a strange tenderness in that kind of erosion. It is not gentle in the moment. A stone falling down a crater wall in vacuum is still a violent thing for the ground it strikes. But from orbit, the total effect is quiet. A sharp rim lowers, a shadow softens. A wall that once stood newly broken becomes less severe. The moon keeps the original violence, then slowly folds it into the texture of the surface. Kepler's landslides also show how difficult it is to call the moon dead. A dead world, in the simplest sense, would no longer change except by being struck from outside. The moon is close to that, but not completely. It reacts to those strikes. It moves material. It lets slopes fail. It stores each adjustment in marks that can be seen from orbit. There is no biology, no rain cycle, no active plate tectonics, and yet the surface is still being edited. The editing is small enough to require patience. A single dark streak on a crater wall may represent material disturbed by an impact no larger than a thrown stone. Another may have waited ages before sliding, held in place by friction until one vibration, one thermal crack, or one tiny collision changed the balance. The wall does not need much. On a world where nothing binds the dust with moisture or roots, a slope can remain ready for a very long time. Kepler is only one crater, but it stands for a wider truth. Across the moon, crater walls carry the evidence of motion. Some slopes show boulder tracks, where stones have rolled down and left winding paths behind them. Some floors hold piles of fallen debris. Some rims have been quietly rounded, not by storms, but by the repeated settling of a surface that is never entirely safe from disturbance. The moon's silence can make motion feel impossible. But motion is there, written in darker dust, in fallen blocks, in softened rims, and in the gradual descent of material from high ground to low. The airless landscape does not change quickly. It changes in whispers of stone. From a distance, the crater remains a bright ring on a grey plain. Up close, it becomes a place where gravity still works, where loose ground still waits, and where even the smallest impact can begin a slow fall down a silent wall. Some lunar craters look as though they were pressed into the ground from directly above. Their rims are nearly circular, their floors sit near the center, and their rays stretch outward in a balanced pattern. Messier crater is not like that. It lies on the lunar surface as a long, narrow wound, stretched in one direction, with a floor that looks more like a slit than a bowl. The shape is the first clue. Most impact craters are round, even when the incoming object arrives at an angle, because the energy of the collision spreads outwards so violently that the direction of arrival is almost erased. The rock does not have time to respond like soft mud receiving a thrown pebble. It is shocked, crushed, heated, and blasted away. The explosion of energy matters more than the exact shape of the object that struck. That is why round craters cover the moon in such great numbers, but when an impactor comes in very low, skimming close to the surface before it strikes, the direction begins to survive in the scar. The collision is no longer centered neatly downward, it is dragged across the ground. Material is thrown unevenly, the crater becomes stretched, and the surrounding debris begins to point back toward the motion that made it. Messier belongs to this rare class. Its elongated form suggests an object arriving at a shallow angle, less than 15 degrees above the surface. At that angle, the incoming body would have crossed the moon's black sky, almost sideways, closing the final distance in a path that barely lifted above the horizon. There would have been no air to slow it, no fire trail in an atmosphere, no sound spreading ahead of it. Only a stone, or a group of stones, moving with enormous speed toward a surface that could not move away. The crater itself is only part of the evidence. Around Messier, the rays tell the rest of the story. Rays are streaks of brighter material thrown out during an impact. They form when crushed rock from below the weathered surface is excavated and scattered across older, darker ground. On a typical fresh crater, rays may spread in many directions, like pale spokes from a wheel. Around Messier, the pattern is not balanced. Debris reaches north and south from one part of the formation, while another bright streak runs strongly westward. The ground is recording direction. Near Messier lies a second companion crater, often discussed with it because the two are tied together by the same strange event. One appears fresher, the other looks older, as if time has softened it more heavily. At first glance, this might suggest two separate impacts divided by a long interval. One crater formed, waited under the slow darkening of space, and then another arrived nearby much later. The ray pattern argues against that simple reading. The older-looking crater may not be much older at all. It may have been covered by material thrown from the second impact, coated with ejecta in a way that made it appear more worn, more muted, and more ancient than it really is. The surface did not age evenly. It was aged by burial. There is another possibility hidden in the shape of the system. The incoming object may have broken apart before impact, splitting into several pieces that struck the surface in rapid succession. Without an atmosphere, the breakup would not have happened through burning friction in the way meteors break over Earth. It may have come from earlier stress, rotation, weakness in the body itself, or tidal forces during its approach. By the time the fragments reached the moon, they were still close enough in space and time to carve a connected pattern. 3 impacts, or a fragmented impact, can explain the odd arrangement of craters and rays. The pieces did not fall straight down. They grazed the surface, striking at such a low angle that the ejecta was thrown along preferred paths rather than evenly around the site. One part of the ground was gouged into a narrow crater. Another was covered by debris from the companion strike. The whole formation became a record of movement rather than just collision. Low-angle impacts are especially valuable because they preserve the direction of arrival more clearly than ordinary craters do. They are like footprints left by objects crossing the solar system, caught at the final instant when orbit becomes geology. The moon, with no thick atmosphere to destroy small incoming bodies before they strike, keeps more of those marks than Earth can. On Earth, the same object might burn, fragment, explode in air, or be erased later by weather and plate motion. On the moon, the path can remain written in stone. Inside the Messier system, other details deepen the scene. Some areas on the crater floor are thought to contain impact melt, rock that became liquid during the collision and then cooled quickly in place. Impact melt can gather in pools, run down slopes, or crack as it freezes. It is lava-like in appearance, but it is not born from a volcano. It is made by violence from above, by pressure and heat arriving in a blink. There are places near the crater where material seems to have flowed after the impact, moving across the floor before solidifying. There are also areas that appear to have sagged or collapsed, as if the shocked ground lost support beneath itself. The crater is not just an empty hole. It is a small landscape of melted stone, fallback debris, fractured crust, and directional rays. The event that made Messier lasted only moments. The object crossed the last stretch of space, struck the ground at a glancing angle, broke or scattered its force across the surface, and sent bright material outward in narrow fans. The heat faded, the molten patches froze. The dust settled. Then the moon returned to silence, but the shape remained. From orbit, Messier is a reminder that the moon does not only preserve where impacts happened, it can preserve how they happened. Direction, angle, fragmentation, burial, flow, and collapse are all still there for a careful camera to read. A crater that looks misshapen is not a mistake in the landscape. It is a sentence written by motion. The trail of that motion points across the lunar surface, westward through pale rays, through the shadowed edge of an elongated floor, through a second crater made old by the debris of its neighbor. Nothing moves there now in any visible way, yet the mark itself still carries the memory of speed. Not every crater begins on level ground. Some impacts strike plains, where the surface offers a broad, even stage for the violence to spread. Others arrive over terrain that is already broken, raised, tilted, or folded by older events. The moon is not a smooth sphere. Its highlands rise in battered regions of pale crust. Its basins sink under old sheets of dark basalt. Its crater rims overlap. Its mountains stand in rings around ancient impacts, and many of its slopes were already steep long before the next stone fell from space. When an impactor strikes a slope, the scar it leaves can become difficult to read. A round bowl may stretch to one side. One wall may stand higher than the other. The floor may appear off-center. The debris may fall farther downhill than uphill, because gravity gives the moving material an easier path in one direction. The crater is shaped not only by the incoming object, but by the land it meets. One lunar crater shows this clearly. From one angle, it looks as if two impacts may have merged, or as if a single object broke apart just before reaching the surface. The outline is uneven. The rim does not have the balanced form expected from a simple strike into flat terrain, but when the surrounding topography is examined, the reason becomes quieter and more geological. The crater sits on the edge of a peak. Before the impact, that place may have been one of the highest points in the local landscape. A mountain or ridge rose from the older lunar ground, catching sunlight along its upper slopes, while lower regions lay in shadow. Then an object arrived. It did not merely dig into a plain. It cut into relief that already had height, direction, and steepness. The crater is partly the mark of a collision, and partly the mark of a mountain being removed. The thought is simple, but it changes the scale of the event. A peak that had stood through long ages of lunar time was struck and reshaped in moments. Stone that had once formed an elevated summit was crushed, melted, thrown outward, and dropped back in a new pattern. The place did not merely receive a hole, it lost part of its former shape. The moon's lower gravity allows mountains and crater walls to stand in ways that would feel strange on Earth. Slopes can remain steep, Cliffs can last for long periods without rain, frost, roots, or flowing water to break them apart. A ridge may preserve its outline for billions of years unless later impacts disturb it. But when an impact does arrive, the lack of atmosphere means there is no softening before contact. The object does not slow through air. It does not burn away into a long, glowing trail. It reaches the ground with most of its cosmic speed intact. On a steep lunar slope, that energy is unevenly received. The uphill side resists differently from the downhill side. Material excavated from the crater can fall away into lower ground. Shock waves move through rock that is not arranged in a flat layer, but angled across a mountain face. The crater becomes a record of three things at once: the incoming path, the strength of the impact, and the pre-existing shape of the land. This is why lunar images can be misleading when seen without elevation data. A photograph may show a distorted crater and invite a simple answer. Perhaps two objects struck. Perhaps the crater is not one crater at all, but a topographic map adds another layer of meaning. It shows height. It shows the slope beneath the sunlight and shadow. It reveals that the crater sits at the margin between high ground and low ground, where impact energy could not spread symmetrically. The same principle appears across the moon in many forms. Craters on crater rims often look strange because they form on tilted walls. Small impacts on terraces may produce uneven bowls. Ejecta falling onto slopes may collect in one direction. A crater on the side of a mountain is not only an impact feature, it is also a landslide source, a broken ledge, a trap for shadow, and sometimes a window into the deeper layers of the lunar crust. The mountain itself matters because lunar peaks often come from earlier violence. Many are not volcanic cones in the earthly sense. Some are central uplifts inside large craters, formed when rock rebounded after impact, rising from below like a slow-motion splash frozen in stone. Others are parts of basin rings, ancient rims left from impacts so large that their original forms are difficult to grasp from the ground. A later crater cutting into such a peak is therefore one impact written over another. The moon is full of this overprinting. Its history does not erase cleanly. It stacks. A basin forms. A mountain ring rises. Lava fills nearby lowlands. A smaller asteroid strikes a slope. A later shower of debris peppers the new crater with smaller holes. Fine dust slowly darkens under space weathering. A boulder falls. A shadow lengthens and shortens through the lunar day. The result is a surface where almost no feature belongs to only one moment. A crater on a peak can also reveal hidden material. The impact may cut through the outer layer of weathered regolith and expose brighter, fresher rock beneath. It may break through crust that was buried under later deposits. It may scatter material downhill, creating streaks that point to the slope as much as to the impact. In the right light, the crater becomes a rough cross-section through a place that was never meant to be opened. There is no need to imagine fire in the ordinary sense. The moon has no air for flames to breathe, yet impact brings heat beyond fire. Rock can melt. Dust can vaporize. The surface can flash from cold stillness into a brief state of fluid violence, then freeze again into a new geometry. A mountain can be cut not by a river, not by ice, not by wind, but by a body arriving from space with enough speed to turn solid ground into a temporary liquid edge. Afterward, stillness returns. The peak no longer has its old summit. The crater sits where the slope was broken. Shadows gather differently. Sunlight catches new walls. The surrounding terrain carries fragments of the event in scattered debris and uneven relief. Nothing announces the change now, except shape. From Earth, the moon keeps the same calm face. Its mountains are too small to see without aid, its broken peaks folded into the grey and white patterns of the disk. But from orbit, a crater cut into high ground becomes a quiet lesson in lunar reading. Shape alone is never enough. The ground beneath the shape has its own history. A scar is not only the thing that struck, it is the world that received it. Near the poles of the moon, sunlight behaves differently. Across most of the lunar surface, day and night arrive in long, severe intervals. The sun rises slowly over a horizon with no blue atmosphere above it, climbs through the black sky, and remains there for many Earth days. Then it sinks again, and darkness returns for just as long. The change is not softened by clouds or twilight. Light comes sharply, without air to scatter it. Shadow comes sharply too, black and cold, lying against stone with an edge that looks almost cut. At the equator, this rhythm creates a hard problem for any machine or settlement that must live by solar power. A place can be flooded with sunlight, then abandoned to darkness for nearly half a lunar month. Batteries must endure the long night. Instruments must survive heat, then cold. The surface expands and contracts under a cycle that is slow, simple, and unforgiving. The poles offer another kind of landscape. The moon is only slightly tilted in relation to the Sunday. Because of that small tilt, sunlight reaches the polar regions at a very low angle. It does not rise high in the sky. It skims. It slides across the horizon like a distant fire seen from the edge of a frozen plain. High rims and raised peaks can catch that low light again and again, while nearby crater floors remain hidden in darkness. A mountain may shine while the ground around it lies in night. A ridge may receive long hours of weak but steady sunlight, not because it is warm, but because it stands just high enough above the surrounding shadow. These places are sometimes called peaks of near-eternal light. The phrase sounds more absolute than the reality. No known site on the moon receives sunlight forever. Seasons, local relief, and the changing geometry of the Earth, moon, and sun all interrupt the pattern. But some polar heights receive light for a much greater share of the lunar year than ordinary regions do. A ridge that sees the sun most of the time is valuable on a world where many places must wait through long darkness. From orbit, such peaks can look like islands. The image is not only poetic, it is almost literal in the way light divides the land. The rim of a polar crater may glow along one edge, while the interior below remains completely black. A central peak may rise from a basin of shadow, its upper slopes touched by sunlight, and its base lost in darkness. The surrounding surface can disappear, leaving only bright fragments suspended in a field of black. Stone becomes shoreline, shadow becomes sea. The reason lies in the geometry of the poles. A crater near the lunar equator sees the sun move more fully across the sky. Its floor may be lit during part of the lunar day and dark during the night. But near the poles, a deep crater can hold areas where the sun never climbs high enough to reach the bottom. The rim blocks the low light. The floor remains in permanent or near-permanent shadow, perhaps for millions or billions of years. Above that darkness, a peak only a short distance away may be one of the brightest and most useful places on the moon. This pairing makes the polar regions unlike anywhere else on the lunar surface. Light and dark exist side by side, in their most extreme forms. One slope offers energy. A nearby hollow may preserve cold. One ridge may become a natural platform for solar arrays. One crater floor below may hold materials that have not felt sunlight since before many landscapes on Earth took their present form. For future exploration, that contrast matters. Solar power is not a small detail on the moon. It is the difference between instruments that sleep through darkness and instruments that continue to work. It is the difference between a temporary visit and a place that can be maintained for longer periods. A sunlit height near the pole could support communications equipment, power systems, or observation stations. It could become an anchor point in a landscape, otherwise divided by deep, cold, and hard shadow. The light itself would not feel generous. There is no warmth in the human sense of a sunny afternoon. The sun remains low, and the ground still belongs to an airless world. A person standing there would see no blue above, no golden haze, no softened horizon. The sky would be black beside the Sunday. The shadows would be absolute where they fell. A nearby slope could be bright enough to power machines, while a crater floor below could be colder than almost any natural place on Earth. This is the kind of closeness that makes the polar moon so strange. Useful sunlight and preserved darkness are neighbors. They do not blend. They do not gradually fade into one another as they might under an atmosphere. The moon draws a hard line between them. Seen from a spacecraft, the poles become a study in edges, bright rims, black floors, thin lines of illumination moving slowly across broken ground, high points that hold the sun a little longer than their surroundings, depressions that may never release their cold. Every small change in height matters. A few meters of relief can determine whether a surface receives sunlight or remains hidden. A ridge becomes important not because it is high by earthly standards, but because it rises in the right place under the right geometry. This is also why maps of the polar regions have become so important. A simple photograph is not enough. The moon must be measured by light over time. Which slopes stay bright longest? Which crater floors remain dark? Which routes connect one usable place to another? Which shadows are brief? And which are ancient? The answer changes with season and angle, and with the exact shape of the ground. The old idea of the moon as a uniform grey desert cannot survive there. Near the poles, it becomes a world of sharp contrasts and hidden resources, a place where survival may depend on standing between light and darkness, close enough to use one without losing access to the other. The islands of polar sunlight are not warm sanctuaries. They are exposed ridges on a cold body in space. But they may be among the most important places humanity has ever mapped beyond Earth. They show that on the moon, even sunlight is a local resource, gathered by height, protected by topography, and separated from darkness by the rim of a crater. And below those bright edges, in places where the sun does not reach, another record is waiting. Below the bright polar ridges, the moon keeps places where morning never arrives. They are not caves in the ordinary sense. They are not tunnels, not hidden chambers, not openings into some imagined underworld. They are crater floors, steep hollows, and small depressions placed so close to the lunar poles that the sun remains forever too low to reach them. Light slides over their rims. It touches nearby heights. It passes across broken slopes, only a short distance away, but the deepest parts remain black. These are the cold traps. The name is plain, almost technical, but the reality is one of the strangest environments near Earth. In most places on the moon, sunlight heats the surface during the long lunar day, and the night lets that heat escape into space. Temperatures swing across a range that would destroy unprotected instruments and turn ordinary engineering into a careful act of survival. In the cold traps, the cycle is broken. Without sunlight, the ground can remain at temperatures so low that water molecules arriving there may not easily leave again. A molecule of water on the open lunar surface is vulnerable. It can be struck by sunlight, lifted by heat, broken apart by radiation, or moved by tiny interactions with the surface dust. The moon has no thick atmosphere to hold it, no pressure to protect it, no weather system to gather it into clouds or rain. Water does not behave there the way it behaves on Earth. It is scattered, fragile, and difficult to keep. But if a water molecule finds its way into a permanently shadowed crater, the story changes. The cold becomes a kind of lock. The molecule may freeze onto a grain of soil, or settle into a thin frost hidden among darker material. Once there, it can remain for very long spans of time, shielded from direct sunlight by the shape of the land itself. The crater is not a container with walls in the human sense. It is a shadow shaped by geometry, and the shadow is doing the holding. This is why the polar moon has become so important. The surface is no longer just stone and dust. It may also be a record of volatile materials, substances that normally vanish easily in sunlight or heat. Water ice in these places may have come from many sources. Some may have arrived inside comets or icy fragments that struck the moon over deep time. Some may have been delivered by micrometeorites. Some may have formed through interactions between the solar wind and oxygen bound in lunar minerals, a slow chemistry occurring across an airless surface. No single source explains everything with complete certainty. The evidence points toward a mixed history. The ice, if preserved in enough quantity, is not only useful, it is historical. A cold trap can hold material from different ages of the solar system, gathered slowly and stored in darkness. It may contain traces of ancient impacts, fragments of chemical stories from the young moon, and molecules that migrated across the surface before becoming trapped. The crater floor becomes less like a mine and more like a frozen archive. It is a place where the moon may have kept what other regions lost. From above, these regions are difficult to see in the usual way. A camera that depends on sunlight sees darkness. The floor may be almost completely black, not because it is empty, but because it is hidden from the light needed to image it clearly. Other instruments must help. They measure temperature, hydrogen, reflected light from nearby surfaces, neutron signatures, and subtle clues in the way the ground responds to radiation. The moon does not give up its coldest records easily. The South Polar region is often spoken of with particular care. It contains deep craters, high ridges, uneven terrain, and many permanently shadowed areas close to places that receive more sunlight. This combination makes it both difficult and valuable. A future landing site must deal with jagged relief, hard shadows, poor visibility, cold pockets, and communication challenges. Yet the same region may offer access to water, ice, and solar power within reach of one another. The landscape is harsh because it is useful. Water changes the meaning of exploration. Carried from Earth, it is heavy. Every kilogram launched upward must be lifted against gravity, pushed through atmosphere, and guided across space. Found on the moon, water becomes part of the local environment, even if extracting it is hard. It can support life directly as drinking water. It can be separated into oxygen and hydrogen. Oxygen can help breathing systems. Hydrogen and oxygen can become rocket propellant. The idea is simple. The practice is not. The ice is not expected to lie in clean blue sheets like a frozen lake under starlight. It may be mixed into regolith, hidden in grains, patchy, buried, or bound in ways that require careful processing. Some regions may have more than others. Some cold traps may hold very little. The moon's water is not a lake waiting in the dark. It is a set of clues spread through soil, shadow, temperature, and chemistry. That uncertainty is part of the reason the cold traps remain so compelling. They sit near Earth, closer than any planet, and still they are not fully known. The nearest world holds places colder and less touched by sunlight than many distant objects. A crater floor at the lunar pole may have been dark since before the first forests grew on Earth, before animals walked on land, before the continents took their present shapes. Above it, the sun has crossed the black sky countless times, never climbing high enough to reach the bottom. There is a quiet contrast in that image. The moon reflects sunlight toward Earth so brightly that it can cast shadows on a clear night. Its near side has guided travelers, poets, farmers, and astronomers for ages. Yet at its poles are small regions that have never taken part in that brightness. They belong to another kind of lunar time, not the monthly rhythm of phases, but the long stillness of cold preservation. A future explorer approaching one of these places would not see a gentle darkness. The shadow would be absolute. The boundary between light and dark could be sharp enough to make distance difficult to judge. Sunlit ground might glare nearby, while the crater interior remains unreadable. Machines entering that darkness would carry their own light, their own heat, their own power. And every step would be a measurement as much as a movement. The cold traps ask for patience. They cannot be understood by looking once. They require maps made across seasons, instruments that can read without sunlight, and landers or rovers able to survive where ordinary warmth is absent. They also require restraint, because the material preserved there may be scientifically precious. Before it becomes a resource, it is evidence. The moon's polar shadows are therefore not empty black spaces at the edge of a map. They are some of the most meaningful places on the whole surface. They hold the possibility of water, the memory of ancient delivery, and the practical question of whether a human presence beyond Earth can learn to live from what is already there. Above them, the ridges keep catching the low Sunday. Below them, the cold remains, holding whatever has fallen into it. The next part of the lunar record lies far from that polar darkness, on the side of the moon that Earth never sees. The far side of the moon was once a hidden hemisphere. For every night that the moon rose over Earth, one face remained turned toward home, and the other stayed beyond direct human sight. The reason is not mystery, but gravity. The moon rotates once in nearly the same time it takes to orbit Earth, so one hemisphere keeps facing this planet while the other looks outward into space. From the ground, the far side could be imagined, calculated, and inferred, but not seen. It was a place without human photographs until spacecraft finally passed behind the moon and returned the first rough images of the unseen half. The far side is not dark. It receives sunlight just as the near side does. Its name only means that it faces away from Earth. For half of each lunar month, the far side is flooded with daylight, and for the other half it lies in night. But emotionally, it still feels hidden, because it was separated from human sight for so long. The familiar Maria of the near side, those broad dark plains visible from Earth, do not dominate there in the same way. The far side is rougher, brighter in many regions, and more heavily marked by old highland crust. Jackson Crater lies on that hidden hemisphere. It is a large, complex crater, about 70 kilometers across, formed by an impact powerful enough to excavate deep material, raise a central peak, and throw fine debris far across the surrounding surface. Its ray system stretches outward for more than 1,000 kilometers, pale streaks laid over older ground like long brush marks of crushed rock. From orbit, those rays make the crater appear young and sharp, even across a landscape already crowded with older scars. A ray system is not merely decoration. It is the visible memory of ejecta, material blasted out during impact and spread across the surface. When the incoming object struck, rock beneath the weathered upper layer was broken, brightened, and launched outward. Some pieces fell close to the rim. Finer material traveled much farther, dusting the surrounding terrain with lighter streaks. Because the moon has no wind or rain to erase them quickly, these rays can remain visible long after the heat of the impact has vanished. Jackson's rays are especially striking because they cross the far side highlands, where the surface already carries a dense record of ancient impacts. The bright lines do not remove the older craters beneath them. They lie across them, adding a newer layer to an older page. This is how the lunar surface often works. It does not clear itself. It accumulates. One event writes over another, and the reader must learn which marks belong to which age. The crater itself is complex in the geological sense. Small craters often form simple bowls. Larger ones behave differently. Their walls slump into terraces, Their floors flatten in places. Their centers rebound after impact, pushing upward into peaks or rings. Jackson has these features. Its walls step downward rather than falling in one smooth curve, and its central region rises from the floor with material that was lifted from below during the violence of formation. That central uplift is one of the quiet wonders of impact physics. A large collision does not simply dig a hole. For a brief moment, the surface behaves in a way that ordinary stone does not seem capable of doing. Rock is compressed, heated, broken, and forced aside. Then the deep floor rebounds upward, like water rising after a drop strikes a pond, except the material is crust, and the timescale is measured in seconds and minutes rather than the slow motion that the final shape suggests. The peak freezes where the rebound stops. In Jackson, elevation adds another layer of strangeness. One side of the crater stands much higher than the other. The surrounding land is tilted, and the crater sits within that unevenness. The eastern side reaches a greater height than the western side, while the floor lies far below both. This makes the crater more than a circular scar. It is a structure built into a sloping part of the far side, where impact and older topography meet. Light can change it completely. An oblique image, taken with the sun low, may make the crater look dramatic and steep, emphasizing terraces, shadows, and the bright central peak. A top-down image taken at another lunar hour can make the same region look darker, flatter, or less obvious. The material has not changed, the sun has. On the moon, where there is no atmosphere to soften illumination, the angle of light controls much of what the eye believes. A small ridge can cast a long black blade of shadow. A rough wall can look smooth when the sun is high. A central peak can glow in one image and sink into darkness in another. This is not a flaw in lunar photography. It is part of the moon's language. To understand the surface, the same place must often be seen under different lighting, different angles, and with elevation data beneath the image. A crater is not only a shape, it is also a relationship between stone, shadow, and sunlight. Jackson teaches that plainly. Its bright scars are real, but their appearance shifts as the sun moves across the black sky. The far side itself carries a similar lesson. For a long time, it was treated in imagination as a kind of blank, opposite to the face seen from Earth. Once seen closely, it became clear that it was not blank at all. It had its own history, its own impact basins, its own crustal thickness, its own roughness, and its own record of bombardment. It was never the moon's empty side, it was only the side that had not yet been read. Jackson's rays stretch across that once hidden terrain like pale lines from a single point of force. They show how far a young impact can reach beyond its rim. They show how fine material can travel across a world without air. They show how the far side, though invisible from Earth, has been shaped by the same long rain of debris that marked the near side. There is a quiet reversal here. The far side may feel remote because it faces away from Earth, but in geological terms it is not separate from the moon's main story. It belongs to the same early violence, the same later impacts, the same solar light, and the same slow darkening by space weather. Its hiddenness was human, not lunar. From Earth, the near side remains the face in the sky. The far side remains unseen without machines. But the moon does not divide itself according to human sight. It keeps both hemispheres in one continuous body, one turning world of highlands, basins, rays, scars, peaks, and shadow. Jackson Crater is one bright sign on that other face, a mark that says the unseen half was never quiet, never empty, and never waiting to become interesting. It was always there, carrying its own bright scars in silence. Some places on the moon are strange not because they are large, but because the eye cannot decide what they are. Ina is one of them. It lies in the Lacus Felicitatis region on the near side, small enough to disappear inside the wider lunar landscape if no one knew where to look. It is only a few kilometers across and not very deep, a modest feature compared with the great basins and bright young craters. Yet in high-resolution images, it can feel more puzzling than many larger formations. Its surface appears broken into smooth patches and rougher textured ground, with shapes that seem to change depending on how the brain reads the light. At first glance, some of its patches may look sunken, like shallow pits or collapsed blisters. Then, after a moment, the same forms can reverse. What looked like a depression becomes a raised surface. What looked like a mound becomes a hollow. The image turns inside out without the ground changing at all. The moon has not moved. The camera has not lied. The eye has simply struggled with a landscape lit in a way that has no earthly softness. On Earth, light is rarely pure. Air scatters it. Dust, water vapor, haze, clouds, and vegetation all add small signals that help the mind judge depth. Shadows are softened by reflected light from the sky. Even in a desert, the atmosphere fills darkness with a little color. The moon offers almost none of that help. Sunlight strikes the ground directly. Shadows can fall black and sharp. A slope tilted slightly toward the sun may glow, while the other side falls into darkness without a gentle middle tone. This makes lunar images beautiful, but also treacherous. A crater can look like a dome if the light direction is misread. A ridge can seem like a trough. A shallow hollow can become a raised bubble in the mind. Rotating an image can change perception instantly because the brain expects light to come from above. When that expectation fails, the moon becomes ambiguous. Ina lives inside that ambiguity. The feature has been described as an irregular mare patch, part of a group of unusual lunar terrains that do not resemble ordinary impact craters, simple volcanic vents, or familiar lava plains. It has a sharp boundary in places, with a floor that appears lower than the surrounding surface. Within it are smooth, rounded patches separated by rougher, hummocky material. The textures are distinct enough to suggest that different processes shaped different parts of the small depression. The age of Ina has been debated because its appearance seems oddly fresh. Some early interpretations suggested that it might represent very young volcanic activity, perhaps far younger than the main era when the moon's dark basaltic plains were formed. That idea carried a quiet surprise. The moon is usually pictured as volcanically active long ago, with its major lava flows ending billions of years in the past. A young volcanic feature would imply that heat lingered in small pockets much longer than expected, but appearances on the moon can mislead. A surface can look young because it has fewer small craters, or because its texture reflects light differently, or because roughness and slope affect how shadows appear. Later studies have offered other possibilities for Ina and features like it. Some suggest that the unusual terrain may result from the collapse or removal of material above subsurface voids. Others consider volcanic gases, foamy lava, or the slow breakdown of fragile deposits. No single explanation has ended the discussion. The honest answer is that Ina remains difficult. That difficulty is valuable. It shows that even close to Earth, on a body photographed in detail from orbit, small features can resist simple classification. The moon is mapped far better than most worlds. But mapping is not the same as knowing every process. A camera can show shape, it can show brightness, it can show texture down to small scales. But the history beneath those textures still has to be inferred, tested, compared, and sometimes left open. Inner also reveals how strongly lunar science depends on perspective. A top-down image shows patterns, an oblique view shows relief, a low sun reveals shadows, a high sun emphasizes brightness and color differences. Each view gives something and hides something. The most useful truth usually emerges not from one image, but from many, taken under different conditions and read together with elevation data, mineral information, crater counts, and thermal measurements. This is a slower kind of seeing. On the moon, light does not simply reveal the land. It participates in the mystery. The same patch of ground can look smooth in one image and rough in another. A shallow depression can become obvious when the sun is low, then nearly vanish when the sun rises higher. A bright surface may be fresh rock, or a difference in grain size, or a slope facing the light, or material with a different composition. The eye begins the work, but it cannot finish it alone. Small craters nearby add another layer to the problem. Some look inverted at first glance, like little domes scattered across the surface. Rotated or seen with the light direction understood, they return to being hollows. This simple visual flip is a reminder that lunar landscapes are often read from shadows, and shadows require trust in the direction of illumination. Without that trust, even a familiar crater can become uncertain. Ina is not dramatic in size. It does not dominate a hemisphere. It does not cast rays for hundreds of kilometers. It is not a mountain ring or a polar cold trap. Its importance is quieter. It is a small region where the moon refuses to be reduced to a single process. It may be volcanic, it may be collapse, it may involve gas, fragile crust, unusual regolith, or a combination still not fully described. The feature waits inside its small boundary, asking for more patient instruments and more careful light. There is something fitting about that. The moon, so visible from Earth, still contains places that are not easy to see correctly. Familiarity has never made it simple. A person can look up and recognize the whole disk. Then a spacecraft can look down and find a patch only a few kilometers wide that unsettles the meaning of shadow and shape. Ina is one of those reminders. The moon is not only a record of force, it is also a record of perception. Its surface can deceive without intending to. It can turn hollows into domes, age into youth, smoothness into mystery, and a small depression into a question that remains open under the cold light of the Sunday. Beyond that puzzle of light and texture, other lunar floors hold marks that are less ambiguous but deeper in meaning. Long fractures where the crust was pressed from below and never quite broken open. Komarov crater holds a different kind of mark. It is not strange because of a ray system reaching across the moon, or because its shape has been stretched by a low impact. From a distance, it could pass as another large lunar crater among many others, a wide scar set into the far side highlands. But the floor tells another story. Long fractures run across it, cutting through the basin in broad, dark lines, as if the ground once came under pressure from below and cracked without ever fully opening. The crater is large enough to belong to the class of complex craters. Its walls are not simple slopes. Its interior has been modified by collapse, uplift, and later movement. But the fractures on the floor are the feature that draws attention. They cross the base in patterns too large to be dismissed as surface scratches. Some are hundreds of meters deep. Some are kilometers wide. They are not small cracks in a thin skin of dust. They are structural wounds in the crust. A fresh impact crater begins with violence from above. Komarov began that way too. An incoming body struck the moon, excavated rock, threw debris outward, and left behind a broad basin. The heat and shock of that moment shaped the first version of the crater. Walls slumped. The floor settled. Material that had been melted by the impact may have gathered in low places before cooling. Then, after that initial event, another process seems to have affected the crater from beneath. The leading explanation is magma. Long ago, when the moon still carried more internal heat, molten rock could collect under parts of the crust. In some regions, it found a way to the surface and spread outward as dark basaltic lava. Those flows made the Maria visible from Earth, the great plains that early observers mistook for seas. In other places, magma rose but did not erupt. It pressed upward against the underside of the crust, adding stress to rock that was already weakened by impact. Komarov appears to belong to that quieter class. Magma may have intruded beneath the crater floor around 2,600,000,000 years ago, building pressure below the surface without breaking through. The floor, trapped between the weight of the crust above and the expanding force beneath, fractured. Long cracks opened across the basin, but the magma never flooded them from below, or at least did not fill them in the way lava filled other lunar plains. The result is a crater floor that looks unfinished, as though the moon began an eruption and then stopped before the surface could release it. That restraint gives the place its character. A volcanic plain shows what happens when molten rock escapes. Komarov shows what happens when it almost does. The fractures are called floor-fractured crater features, and they appear in several places on the moon. They are especially useful because they connect impacts with later internal activity. The crater itself creates a weakness, a low place where the crust has been broken, heated, and thinned. Magma rising later may find that damaged zone easier to deform. Instead of building a volcano in the familiar earthly image, the moon lifts and cracks the old impact floor. There is no need for a cone, no ash plume, no glowing river. Lunar volcanism often leaves quieter signatures. A smooth, dark mare plain, a winding rill, a low dome, a vent surrounded by darker deposits, a fractured crater floor. The moon's volcanic past is not always written as a mountain with smoke above it. More often, it appears as texture, color, elevation, and the shape of cooling rock. Komarov belongs to the language of pressure, not eruption. The absence of atmosphere makes the scene harder and more exact. If magma had reached the surface, it would not have steamed under air or sent a plume into a blue sky. It would have met vacuum. Gases would have expanded rapidly. Lava would have cooled under open space. But in Komarov, the most important action may have remained hidden. The molten rock stayed below, close enough to break the surface from underneath, not close enough to pour across it. This makes the crater a kind of locked door in lunar geology. Something pushed against it. The door cracked. It did not open. The scale of the fractures is easy to lose when seen in an image. On a screen, they become lines. On the ground, they would be enormous troughs and broken walls, places where the floor dropped or pulled apart under stress. Their shadows would change slowly through the lunar day. Their edges would catch sunlight. Loose material would gather at their bases. A rover moving near them would face not a delicate crack, but a landscape obstacle. The fractures also show that the moon's interior did not cool all at once. Heat remained unevenly. Some regions became quiet early. Others kept enough warmth for magma to rise long after the most intense era of lunar formation had passed. This uneven cooling matters because the moon is small compared with Earth. A small world loses heat more easily. Its geological activity fades sooner, yet places like Komarov show that fading is not the same as instant silence. The interior can keep pockets of motion after the surface already looks old. The crater floor, therefore, records a conversation between two times. The first time is the impact age, when the crater was opened by a body falling from space. The second time is the volcanic age, when heat from within returned to the same wound and changed it. One event came from outside, one came from below. Together, They made a feature that neither process would have made alone. This layered history is one of the moon's quiet strengths as a scientific world. Its surface does not only show isolated events, it shows how one event prepares the ground for another. An impact can thin and weaken the crust. Later magma can exploit that weakness. A fracture can expose material. Later, small impacts can scatter it. Each process leaves conditions for the next, and the surface becomes a slow record of cause and response. Komarov is not as visually simple as a bright young crater with long rays. It does not offer the easy drama of a fresh scar. Its meaning is slower. The eye must spend time on the floor, following the broken lines, imagining the force underneath them, recognizing that the moon once held pressure below a surface that now appears dry and cold. The crater rests in silence today. The magma that stressed its floor has cooled or retreated. The fractures remain open as geometry, not as motion. Dust lies along their edges. Small impacts mark the fractured planes. The low sun turns their relief into dark bands and pale walls. A crater made by falling stone became a place shaped by buried fire. Komarov keeps that memory in its broken floor. Some of the moon's old rivers did not carry water. They carried lava. Today, the lunar surface looks dry beyond comparison. It has no oceans, no streams, no clouds gathering over mountains, no rain darkening the dust. The dark plains visible from Earth are stone, not sea, yet their smoothness comes from a time when molten rock spread across low ground and filled enormous basins with basalt. The moon once had flows that moved, pooled, cooled, cracked, and left behind channels that still curve through the surface. West of Plato Crater, near the northern part of the visible moon, the land keeps one of these records. Plato itself is a large crater with a dark, smooth floor, a flat-shadowed basin that can be seen through small telescopes from Earth. Its interior was likely flooded by lava long after the original impact opened the crater. The molten rock covered older irregularities, cooled into a level floor, and gave Plato the calm, dark appearance that makes it so recognizable. Nearby, the surrounding terrain is less calm. A channel cuts through the ground, narrow in comparison with the great crater but large enough to be seen clearly from orbit. It begins near a vent, an opening or source region where molten material once reached the surface. From there, the channel extends away, tracing the path of ancient flow. It is called a rill, a lunar groove or channel, often linked to the movement of lava across the surface. The comparison to a river is useful, but incomplete. A river on Earth is shaped by water, gravity, sediment, climate, and the steady renewal of rain and meltwater. It changes season by season. It carries mud, plants, fish, and reflected sky. A lunar lava channel was something else entirely. It flowed under black space, across a world with no air, no sound carried through atmosphere, and no water to cool it from above. Its surface may have crusted over, while hotter material moved underneath. Its edges may have been eaten away by heat. Its floor may have been cut, melted, or drained as the flow advanced downhill. The rill near Plato is a reminder that the moon's dryness is a late condition, not the whole story. The surface is dry now, but it was not always cold. Heat from the young lunar interior once escaped through fractures and vents. Molten basalt rose and spread across low regions, creating the maria that darken the near side. These flows were not oceans, but from Earth they gave that impression, broad and dark enough to be named as seas by early observers who did not know they were looking at frozen fire. The scale of lunar volcanism is easy to underestimate. The maria cover huge areas. Some flows may have traveled long distances across basin floors, filling depressions and burying older craters. layers of basalt stacked over time, one eruption after another, until parts of the moon's face were resurfaced into smoother plains. The highlands remained brighter and more heavily cratered, while the low basins became darker and flatter. A rill is a more intimate trace of that same volcanic world. It shows not only that lava existed, but that it moved with direction. It had a source. It followed slope. It cut or occupied a path. It left behind a shape that can be followed like a line of thought across the ground. In a landscape dominated by circular scars, a winding channel feels different. It is not the mark of something falling. It is the mark of something flowing. Around Plato, the lava story is mixed with collapse. Along one side of the crater, a large slump block marks where a section of crust broke away from the wall and dropped downward. It may once have been connected to higher terrain, part of the crater rim or nearby plain, before gravity and structural weakness pulled it lower. The block is not small. On Earth, a collapse of that scale would be a regional event. On the moon, it sits in silence. A broad piece of wall shifted from its former place and preserved under the unchanging sky. This combination of lava flow and wall collapse shows how lunar landscapes are built from more than one process. Plato began with an impact. Later, lava filled its floor. Nearby vents released molten material. Channels formed where lava moved. Slopes failed where rock could no longer hold its position. Smaller craters arrived afterward, punching into the new surface. Each event changed the meaning of the one before it. The smoothness of a lava-filled crater can hide enormous violence. A dark floor looks peaceful from a distance. It may even look simple, as though the moon placed a flat surface inside a ring and left it there. But the flatness is a cover. Beneath it may be buried craters, old fractures, cooled flow fronts, and layers of basalt stacked across time. The calm surface is the final state of movement that once had heat, pressure, and direction. There is also a difference between lava that erupts and lava that remains trapped below. Komarov's cracked floor suggested magma pressing upward without reaching the surface. Near Plato, the record is more open. The vent and rill show that molten rock escaped. It found a route. It carved or occupied a channel and then ceased. The moon holds both outcomes, buried pressure and released flow. Neither resembles Earth's active volcanism today. There are no glowing rivers moving across the moon now. The major age of widespread lunar volcanism ended long ago. The vents are quiet. The channels are empty. The flows are stone, but their shapes remain clear because the moon has not erased them. A riverbed on Earth can be altered by the next flood, overgrown by forest, or cut by human roads. A lunar lava channel can sit for billions of years, its curve still readable under low sunlight. The rills also help explain the uneven face of the moon. The near side is rich in dark maria, while the far side has far fewer. The reason is tied to differences in crustal thickness, heat distribution, and the history of the Great Basins. Lava found broad places to spread on the near side, making the face seen from Earth darker and smoother in large patches. That familiar pattern is not just decoration, it is geology visible to the naked eye. The moon's ancient lava does not make the world feel less barren, it makes the barrenness older and more layered. The dry channels are not evidence of life, or rain, or habitability. They are evidence of internal heat fading through stone. A small world, born hot, lost its warmth slowly enough that molten rock once moved across its face. Then the movement ended, and the shapes were left behind. Near Plato, the silent rill still points away from its vent. The dark floor of the crater still holds the memory of flooding. The collapsed wall still rests where gravity placed it. Nothing flows there now. The river has become rock, and the rock has become a line across the moon's cold skin. Aristarchus is one of the brightest stars on the moon. Even from Earth, without a spacecraft, and without crossing the space between worlds, it can draw the eye. It sits in the northwestern part of the near side, a pale crater set against older, darker terrain. Through a telescope, it appears almost too bright for its surroundings, as though the lunar surface has been freshly opened there and has not yet had time to darken under the slow touch of space. Brightness on the moon is often a clue. Fresh material tends to be lighter because it has not been exposed for as long to space weathering. The gradual darkening caused by micrometeorite impacts, solar wind, and radiation. Older surfaces lose some of their sharp contrast. They become muted. Newer surfaces reveal cleaner rock and dust from below. Aristarchus glows because it has uncovered something. The crater is not one of the largest on the moon. Its diameter is only about 40 kilometers, far smaller than the great basins that shape whole regions of the lunar face. But size is not the only measure of importance. Aristarchus is young enough, bright enough, and complex enough to offer a clear view into how an impact can transform solid rock into a temporary world of heat, flow, collapse, and exposure. When the object that made Aristarchus struck the moon, the ground did not simply crack and settle. The impact released enough energy to melt parts of the target rock. For a short time, stone became liquid. The melt gathered on the crater floor, moved along slopes, and froze into sheets and patches that still carry the memory of flow. This is impact melt, not volcanic lava, though the two can look similar after cooling. Lava comes from inside a world. Impact melt is made when the force from outside becomes strong enough to liquefy the surface itself. That distinction matters. The moon has both kinds of melted rock in its history. Its maria were made by lava, rising from the interior and spreading across basins. Aristarchus shows the other path. A body falls from space and makes its own brief heat. The liquid does not come from a deep magma chamber. It is born in the collision. From an oblique view, the crater has the grandeur of a broken bowl. The rim rises sharply. Shadows stretch from the walls. The floor lies far below, and the central uplift stands within it as a small, rugged mass compared with the larger crater around it. From high above, the details become more exact. The walls are terraced, where large sections have slumped inward after the impact. The floor shows smooth regions where melt once pooled. Cracks cross some of those surfaces, formed as molten rock cooled, contracted, and hardened. Cooling leaves marks. A liquid sheet of rock does not become solid without stress. As the upper surface loses heat to space, it stiffens. The material beneath may still be warmer. The sheet contracts. It fractures. Thin lines open across the frozen floor, not because water dried there, not because mud cracked under sunlight, but because once melted lunar rock changed volume as it cooled. The result is a pattern of stress written across a crater basin. The central peak adds another layer. It rose because the ground rebounded after the impact. In large craters, the shocked rock below the center can push upward after the initial excavation, lifting material that once lay deeper in the crust. Aristarchus exposes layered patterns in that uplift. Banded textures and variations in brightness suggest that the impact brought buried material into view, placing older rock under direct sunlight for instruments to read. This is one of the gifts of impact craters. They destroy, but they also reveal. A crater cuts through the upper surface and throws deeper material outward. It builds natural windows into layers that would otherwise remain hidden. On Earth, drilling is needed to reach certain depths. On the moon, an impact can do the first violent part of that work, leaving the results open under a black sky. Aristarchus sits in a region already rich with volcanic history. Nearby are sinuous rills, dark deposits, and landforms connected with ancient eruptions and flowing lava. The crater did not form on a blank surface. It struck a landscape that had already been shaped by internal heat. This makes the area a meeting place between two kinds of lunar fire: the old fire from below and the sudden fire from above. The contrast is quiet but powerful. Volcanic activity works from the inside outward. Pressure builds below. Molten rock rises, finds weakness, and spreads if it can. Impact works from the outside inward. A body arrives from space, compresses the surface, melts it, excavates it, and leaves behind a scar that exposes what was below. In Aristarchus, these stories sit near each other, and the surface becomes difficult to reduce to one origin. The crater's brightness has also made it a source of human attention for a long time. Some observers in the past reported temporary glows or color changes in the Aristarchus region, part of a broader class of reports sometimes called transient lunar phenomena. Many such observations are uncertain, affected by atmosphere, telescope conditions, human perception, and the difficulty of judging light on the moon. The feature itself, however, remains genuinely bright and geologically rich. The mystery is not that the moon is glowing with some hidden life. The mystery is how many different processes are gathered in one small region of the surface. Under low sun, Aristarchus becomes almost sculptural. Shadows reveal the steepness of the walls. Bright slopes stand beside dark hollows. Melt deposits appear smoother than the broken ground around them. The rim throws long shapes across the floor. The crater looks newly opened, though its age is still measured on a scale far beyond ordinary human history. A person standing on the floor would not see the neat circle visible from orbit. The walls would rise in broken terraces, pale and dark depending on the angle of light. The central peak would be a rough highland of exposed material. The ground underfoot might include glassy fragments, shocked minerals, and fine dust made from crushed rock. There would be no sound in the open vacuum. A stone kicked from a ledge would fall without a rustle, strike the ground, and send grains outward in silence. Impact melt would not look like flowing liquid now. It would be hard, cold, and old, but its surface would still carry the evidence of having once moved. A smooth patch at the base of a slope, a frozen tongue of material, a cracked floor, a boundary where melt met rougher debris and stopped. These are the after-images of heat. Aristarchus shows that a crater is not simply absence. It is not just missing ground. It is a place where the moon was briefly rearranged into states that no longer exist there. Flowing rock, rebounding crust, collapsing walls, falling debris, and fresh material exposed to space for the first time. The crater is a frozen moment after an event too fast to witness and too old to remember. From Earth, it remains a bright fleck on the moon's face. From orbit, it becomes a basin of melted stone and opened layers. In its pale walls and fractured floor, the moon keeps one of its clearest reminders that even cold rock can carry the shape of fire. Not every lunar mystery is carved downward into the ground. Some are drawn across it. Reiner Gamma lies on the near side of the moon, in the broad, dark region of Oceanus Procellarum. It is visible to telescopes from Earth as a pale, unusual marking near the western limb, a shape that does not behave like a crater, a mountain, or a lava channel. It has no obvious rim, no deep bowl, no central peak, no raised wall casting a neat shadow across the floor. Instead, it appears as a bright, looping pattern laid over the surface, like a faint white current frozen into the dust. These patterns are called lunar swirls. The name is unusually gentle for a geological feature, and in this case, it fits. Lunar swirls are bright, sinuous markings that wind across the surface in curves and wisps. They can look almost painted, as if some invisible brush moved across the moon and left pale trails behind. Reiner Gamma is the most famous of them, not because it is the only one, but because it is especially clear, especially beautiful, and especially puzzling. The first odd thing about a swirl is what it does not do. A crater changes the shape of the land. A rill cuts a channel. A scarp raises one side of a fault above another. A volcanic flow smooths a surface and buries older ground. Reiner Gamma seems different. Its bright markings cross the terrain without forming obvious topography. They lie over craters and older deposits, following a pattern of brightness more than elevation. The ground is marked, but not deeply sculpted. That makes the mystery subtler. Something has changed the surface, but not by digging it up. Brightness on the moon often tells a story about age. Fresh material is lighter. Older material becomes darker through space weathering as micrometeorites strike it. Solar wind particles alter it, and tiny bits of glass and metal accumulate in the regolith. Over time, the exposed surface matures. It loses the clean brightness of newly uncovered material. A young crater can therefore appear bright simply because it has excavated fresh rock. Reiner Gamma complicates that rule. Its bright markings do not come from a fresh impact crater at the center. They are not arranged like ordinary rays. They curve, loop, and twist in a way that suggests the surface has been protected or altered unevenly. Some parts appear optically young, while nearby darker lanes appear more weathered. The moon seems to have aged differently across a small area, as though invisible forces shielded one patch and exposed another. The key clue is magnetism. The moon does not have a global magnetic field like Earth does today. There is no worldwide magnetic shield surrounding it. No large magnetosphere deflecting the solar wind around the entire body. But the lunar crust holds local patches of magnetized rock. These are magnetic anomalies, remnants of ancient processes that left parts of the crust carrying their own weak fields. Reiner Gamma sits above one of the strongest known of these anomalies. That connection may explain the swirl. The solar wind is a stream of charged particles flowing outward from the sunday. On Earth, the planet's magnetic field guides much of that stream around the atmosphere, creating a vast protective region. And, near the poles, auroras. On the moon, with no global shield and almost no atmosphere, the solar wind normally reaches the surface directly. It helps darken and mature the regolith over long periods. Grain by grain, exposure changes the way the surface reflects light. But over a magnetic anomaly, the solar wind may be partly deflected. The local magnetic field does not protect the whole moon. It is far too small for that. Yet it may create a miniature magnetic shelter above a patch of ground, a tiny region where charged particles are steered away or concentrated differently. Where the solar wind is reduced, the surface may stay brighter for longer. Where particles are focused, the surface may weather more strongly, producing darker lanes beside the pale swirls. In this view, Reiner Gamma is not a deposit placed on top of the moon. It is a pattern of uneven aging. That is a very quiet kind of geology. No mountain rises, no lava pours, no crater opens. The surface changes because space itself interacts differently with one patch of dust than with another. A magnetic field too weak to move a compass needle in any ordinary human scene may still be strong enough, over millions of years, to write a pale shape across the regolith. The image becomes more delicate the longer it is considered. A swirl is not merely a mark on stone, it is the visible footprint of an invisible boundary. The bright curves may show where charged particles were kept away. The darker lanes may show where those particles were redirected. The entire feature may be a map of solar wind meeting ancient magnetism above an airless surface. Yet the answer is not complete. Lunar swirls remain open questions. Scientists continue to study whether magnetic shielding alone explains their shapes, or whether other processes also contribute. Some ideas involve comet impacts, dust movement, electrostatic effects, or unusual properties in the regolith. The strongest evidence still points toward a deep relationship between swirls and crustal magnetic anomalies, but the details of how those elegant forms become so sharply drawn are still being worked out. That uncertainty is part of Reiner Gamma's power. It is near enough to be seen from Earth. It has been photographed from orbit. Its brightness is plain. Its magnetic anomaly is measured, and still, the feature is not fully settled. The moon can be mapped in high resolution and still keep a small, pale question on its face. Future instruments are meant to go closer. A surface mission to Reiner Gamma can measure the magnetic field directly from the ground, examine the local plasma environment, and study the regolith where the swirl is bright and where it is dark. From orbit, the feature is graceful and remote. On the surface, it becomes a place of grains, charges, fields, and sunlight, where the difference between a pale lane and a darker one may reveal how airless worlds weather under the sunday. Standing there in imagination, the landscape would not look like a painted symbol. The curves visible from above would stretch across low, dusty ground. There might be no cliff marking their edge, no wall to step over, no sudden ridge to show where the swirl begins. The difference may lie in reflectance, texture, maturity, and chemistry. One patch of soil would return light differently from another. The mystery would be underfoot, not rising before the eyes. This makes Reiner Gamma unlike the craters that dominate lunar thinking. A crater announces itself by shape. Reiner Gamma speaks through contrast. It is a feature of brightness, a surface memory of invisible forces. It does not need depth to be meaningful. It does not need height to be real. The moon's story is often told through impact and lava, through fire from above and fire from below. Reiner Gamma adds another chapter, written by magnetism and the solar wind. It shows that the moon is shaped not only by stones large enough to make craters, but also by particles too small to see, arriving constantly from the sun, touching dust for ages, unless something ancient in the crust turns them aside. A pale swirl remains where that turning may have happened. On the familiar face of the moon, among dark plains and bright craters, Reiner Gamma lies like a soft mark left by a force that has no visible body. It is quiet, curved, and unresolved, a reminder that even the surface itself can be a kind of sky, receiving invisible weather from space. The moon still trembles, not often in a way that can be seen from orbit, not with oceans shaking against coastlines, or buildings swaying, or birds rising from trees before the ground settles again. The moon has none of those witnesses. Its quakes move through stone beneath a black sky, through crust that has been cold for ages, across a surface where no air carries the sound of fracture. If a slope shifts, the dust falls silently. If a fault slips, the motion belongs almost entirely to the ground. For a long time, the moon seemed like the kind of world that should have no such motion left. It is small compared with Earth. It cooled more quickly. It has no active plate tectonics, no great moving continents, no ocean trenches where one plate sinks beneath another. Its volcanoes have been quiet for vast stretches of time. Its face appears fixed enough that the same great Maria and highlands have looked back at Earth through all of recorded history. Then the Apollo astronauts left seismometers behind. Those instruments listened after the astronauts departed. They did not listen with ears, but with delicate sensors placed on the lunar surface, waiting for vibration. They recorded different kinds of moonquakes. Some were caused by meteoroid impacts, small bodies striking the surface and sending waves through the crust. Some were linked to thermal stress, as the upper layers expanded and contracted during the long shift from cold night to hot day. Some came from deep inside the moon, repeating with tidal rhythms as Earth's gravity flexed its companion. and some were shallow. The shallow moonquakes are the most important for the surface story. They seem to originate closer to the crust and can be stronger than expected for a world often imagined as completely dormant. Their waves can last longer than earthquakes of similar strength on Earth, partly because the moon is dry and rigid, with less internal softness and less water to damp the motion. A vibration can ring through it in a way that feels almost bell-like, though no sound escapes into space. Across the moon, high-resolution images have revealed long, low cliffs called lobate scarps. They are not cliffs in the dramatic earthly sense of sea walls or mountain faces, but they are clear breaks in the surface. One side is raised above the other. The shape suggests compression, a place where the crust has been pushed together until one section thrusts over another. These are thrust faults, and they carry a quiet message. The moon has contracted. The cause is cooling. A young world begins with heat. Some of that heat comes from formation, from impacts, from radioactive decay, from the deep rearrangement of material as metal and rock separate. Over time, a small body loses that heat into space. As the interior cools, it shrinks slightly. The outer crust must adjust to a body that is becoming, by a small amount, smaller than it once was. Rock resists. Stress builds. Then, in places, it breaks. The total shrinkage is not large compared with the moon itself. It is not a collapse. It is not a visible fading of the disk in the sky. It is a slow tightening across deep time, measured in hundreds of meters over billions of years. Yet stone does not need a large change to leave a mark. A small contraction across a whole world can gather stress into faults. A surface that seems still can wrinkle. Lobate scarps are those wrinkles made visible. They can run for kilometers. Some cut across small craters, meaning the faults must be younger than the craters they disturb. That is a valuable clue. If a scarp crosses an older impact feature without being heavily battered itself, it cannot belong only to the moon's earliest history. It may be geologically young. Some scarps may have formed within the last 100 million years, which sounds ancient in human terms, but recent in the life of a body more than 4 billion years old. The connection between scarps and moonquakes is not only visual. The locations of shallow moonquakes recorded by Apollo have been compared with these young fault scarps. The match is not perfect because the Apollo seismic network was small and the exact locations of moonquakes were hard to determine. Still, the evidence suggests that some faults may be active, or at least recently active, as the moon continues to cool and contract. This changes how the surface is imagined. The moon is not a body where all meaningful geology ended in one distant era. It is mostly quiet, but not absolutely quiet. It still responds to internal cooling. It still feels Earth's tidal pull. It still receives impacts. Its crust still holds stresses that can be released suddenly after long stillness. The South Polar region makes this especially important. That region is attractive for exploration because of its long-lit ridges and nearby cold traps. But the same region also contains complex terrain, steep slopes, deep shadows, and faults. Studies of the shrinking moon have identified faulting and possible moonquake hazards near some candidate exploration areas. For robotic missions, this matters. For future human surface activity, it matters even more. A place chosen for light and water must also be understood as ground. The risk should not be turned into fear. The moon is not shaking constantly beneath every future landing site, but a long-duration presence requires a more careful view than a short visit. Habitats, towers, solar arrays, storage systems, landing pads, and routes for rovers would all need to respect the surface they stand on. A fault scarp is not only a line on a map, it is a sign that the crust has moved before and could move again. There is a deeper lesson in that. Human exploration often seeks stable places, flat ground, steady sunlight, reliable communication, useful resources. The moon offers those things only in pieces. A ridge may be bright but rough. A crater may hold ice but remain dark. A plain may be smooth but far from resources. A polar site may be valuable but geologically complicated. The moon does not arrange itself for convenience, it preserves its own history first. The moonquakes recorded by Apollo were among the first direct hints that the lunar interior was not simply inert. Now, orbiters and modern analysis add context to those old vibrations. Images show faults. Models show contraction. Tidal forces show how Earth continues to pull on the moon's crust. New instruments may one day listen again with far better coverage, placing seismometers in regions Apollo never reached. The moon may have more to say, not with words, but with waves through stone. A moonquake would be unlike an earthquake in feeling and setting. There would be no atmosphere carrying rumble, no loose leaves trembling, no water in a glass. But the ground could shift. Dust could slide. A boulder perched on a slope could begin to move. A fault that had held stress for ages could release it in a moment. And the vibration could travel through the dry crust, fading slowly into the cold body. On Earth, earthquakes are part of a living planet's restless surface. On the moon, quakes are the afterthoughts of cooling, impacts, and tides. They are not signs of a world like Earth. They are signs of a world still adjusting to its own age. This makes the moon feel older and more alive at the same time. Older because its contraction is the long consequence of heat lost since the beginning. More alive because the consequence has not completely ended. The surface still has faults sharp enough to see, scarps young enough to matter, and vibrations strong enough to be measured. A wrinkle in lunar crust can be a kind of heartbeat, slow beyond ordinary imagination. Not the heartbeat of biology, not the pulse of oceans or atmosphere. A colder rhythm, a body cooling in space, tightening by small amounts, and occasionally letting the strain pass through stone. The moon still trembles, and in that trembling, it keeps proving that silence is not the same as sleep. The moon does not only leave marks on its own surface, it leaves marks on Earth as well. They are not cut into stone in the same way as craters. They are written in water, in the slow lift and fall of oceans, in the wet line left on a harbour wall after the tide has turned. Every day, the sea answers the moon. It rises toward the pull of lunar gravity, then lowers again as Earth turns through the tidal bulges that wrap around it. The motion is familiar enough to become background, like the moon itself. A dock stands higher above the water in the morning, then lower by evening. Mudflats appear, then vanish. Boats settle against their ropes and lift again. This is one of the moon's oldest conversations with Earth. The force is gentle in appearance, but planetary in scale. The moon pulls more strongly on the side of Earth nearest to it, drawing the oceans slightly outward. On the far side, another bulge forms as Earth and Moon move around their shared center of mass. The result is not one simple wave following the moon, but a complex pattern shaped by continents, seafloors, coastlines, currents, and the rotation of the planet. The tide that reaches a city or marsh is the final local expression of a celestial relationship. The sun joins the pattern too. Its gravity also pulls on Earth's oceans, though its tidal effect is weaker than the moon's because it is so far away. When sun, Earth, and moon line up during new moon and full moon, their pulls reinforce each other, and the tides become larger. These are spring tides, not named for the season, but for the way the water seems to spring higher. When the sun and moon pull at right angles, the tidal range becomes smaller. These are neap tides, quieter in their rise and fall. Even this is not the whole rhythm. The moon's orbit is tilted compared with the plane in which Earth moves around the Sunday. It does not circle Earth in a perfectly flat path aligned with the ecliptic. Instead, its path crosses that plane at 2 points, called nodes. One is where the moon passes upward through the plane. The other is where it passes downward. These nodes do not stay fixed. They slowly move, completing a cycle in about 18.6 years. The name for this is the lunar nodal cycle. It sounds distant and technical, but its effect can reach shorelines. During part of the cycle, the geometry of the moon's orbit slightly suppresses tidal ranges in some places. During the other part, it amplifies them. The moon is not suddenly stronger. It has not moved closer in any dramatic way. The change is in alignment, in the angle at which the lunar pull works together with the sun and with Earth's oceans. The same old tide becomes a little higher in its high phase, a little lower in its low phase, depending on the place and the timing. For most of human history, this cycle passed through coastal life as one rhythm among many. People noticed tides, storms, seasons, and unusual flood years. But the long nodal pattern did not always stand apart from the rest. It takes careful records, tide gauges, and modern analysis to separate the slow lunar signal from weather, sea level, land movement, and local geography. The moon's influence is steady, but the coast is complicated. The concern now is not that the lunar nodal cycle is new. It is ancient. The concern is that it is returning to a tide-amplifying phase on a planet whose seas are already higher than they used to be. A high tide that once stayed below a street may now come close to the curb. Add a small lunar amplification, and the same tide can cross the threshold. No storm is required. No dramatic wave needs to arrive. Water simply rises high enough, often enough, to enter places built under older assumptions. This is sometimes called high tide flooding, or nuisance flooding, though the second name can make it sound too small. It can close roads, push salt water into drainage systems, damage foundations, interrupt daily travel, and wear down coastal infrastructure by repetition. The water may arrive quietly under a clear sky. It may leave later the same day, but if it returns again and again, the ordinary rhythm of a place begins to change. NASA's sea-level researchers have warned that, during the middle of the 2030s, the tide-amplifying part of the lunar nodal cycle may combine with rising seas to produce sharp increases in high-tide flooding along many coastlines. The moon will not be acting alone. It will be adding its old rhythm to a newer condition created by a warmer world and higher oceans. A natural cycle becomes more disruptive because the baseline has shifted. That is the quiet part of the problem. The moon is doing what it has always done. Earth is not in the same state. Coasts are sensitive because they live near boundaries. A few centimeters can matter. A small increase in sea level can turn a rare flood into a frequent one. A storm drain designed for one tidal range may fail under another. A marsh adapted to periodic flooding may struggle if the water arrives too often or stays too long. A road that once flooded only in storms may begin to flood during certain high tides, then during more of them. The lunar nodal cycle does not strike like an impact. It accumulates through timing. It returns through calendars and water levels. It is not seen as a crater, but as a pattern in records. More days with flooding, higher peaks during certain alignments, clusters of events that appear when astronomical cycles meet local vulnerability. There are living systems that respond in more complicated ways. Salt marshes, mangroves, tidal flats, and coastal wetlands have always belonged to the border between land and sea. Some can grow with sediment if water levels rise slowly enough, and if human development does not trap them in place. Mangroves can reduce wave energy, hold sediment, shelter young fish, and store carbon in waterlogged soils. In some regions, Tidal changes may even help expand certain wetland canopies for a time. Nature does not answer every flood with the same response, but adaptation has limits. A marsh can drown if water rises too quickly or if sediment cannot build the surface upward. A mangrove forest can protect a coast only where it has room to exist. A city built with hard edges, paved ground, and low drainage has less flexibility. The moon's rhythm then meets concrete, asphalt, pipes, basements, electrical systems, and neighborhoods that cannot move easily. This is where knowledge matters. The nodal cycle is predictable. It can be calculated long before its strongest effects arrive. Tide gauges can show which places are close to flooding thresholds. Sea level projections can show where small changes may matter most. Communities can raise roads, redesign drainage, restore wetlands, protect mangroves, adjust building codes, and rethink the line between land and water. The moon does not offer surprise in this case. It offers warning through repetition. There is a strange calm in that. The same moon that preserves frozen shadows at its poles and pale swirls on its surface also pulls on the oceans each day. Its influence crosses the distance between worlds without sound or light. It lifts water in harbors, shapes mudflats, guides spawning cycles, and changes the future of coastal streets when its long orbit aligns with rising seas. The lunar record is not only on the moon, it is on Earth's shorelines, in the return of water, in the patient movement of tides, in the slow recognition that a celestial rhythm can become an earthly problem when the world below has changed. Above the coast, the moon continues its orbit. It does not hurry. It does not pause. The tide goes out, then comes back again. The moon appears to keep one face turned toward Earth. This is true, but only in the broadest sense. The same hemisphere faces home because the moon is tidally locked, rotating once in the same time it takes to complete one orbit. Its spin and its path around Earth are bound together by gravity. Over long ages, tidal forces slowed the moon's rotation until one side remained mostly turned toward the planet that shaped it. Mostly is the important word. The moon does not hang in perfect stillness. It nods, tilts, rocks, and drifts slightly from side to side in the sky. The motion is not obvious on a single night. A full moon rising over a dark horizon looks steady enough to seem fixed. Its maria hold their familiar arrangement. Its bright highlands remain where memory expects them. But across a month, when many images are placed together, the disk begins to move. The moon seems to breathe around its center, showing a little more of one edge, then a little more of another. This motion is called libration. It is not the moon turning freely away from Earth. It is not a break in tidal locking. It is a small geometric gift created by the details of orbit, rotation, and perspective. Because the moon's orbit is not a perfect circle, its speed around Earth changes. It moves faster when it is closer and slower when it is farther away. Its rotation, however, stays nearly steady. This mismatch allows observers on Earth to see slightly around the eastern and western limbs at different times. 1 month reveals a little more of one side. Another moment reveals a little more of the other. There is also a north-south rocking. The moon's axis is tilted slightly, and its orbit is inclined. So the view from Earth alternately looks a little over the lunar north and a little over the lunar south. Features near the edge of the visible disk are not always equally hidden. A crater that clings to the limb can lean into view, then withdraw again. A mountain range can become easier to see under one geometry and nearly disappear under another. The effect is slow and graceful. It is not a dramatic wobble in space, but a changing angle of sight. Still, over time, it matters. Although one hemisphere faces Earth on average, libration allows more than half of the lunar surface to be seen from the ground across a full cycle, not the whole moon. The far side remains mostly beyond direct view, but the visible region is larger than the simple half that tidal locking would suggest. The moon gives away its edges. That edge view has always had a special quality. Near the limb, lunar features are foreshortened, craters look squeezed, mountains stand close to the outline of the disk, shadows fall in ways that are harder to interpret. The surface curves away, and the eye feels the moon's roundness more strongly there than near the center. Libration makes those borderlands shift, bringing some formations closer to view while sending others back toward concealment. The same motion that looks like a gentle rocking is also a reminder that the moon is not an image pasted onto the night. It is a moving body. It orbits, it rotates, it rises and sets because Earth turns beneath it. It changes phase because sunlight reaches it from changing angles. It crosses the sky along a path tilted against the ecliptic. It passes above and below that plane. Its nodes slide slowly through their long cycle. Its distance changes. Its apparent size changes slightly. Its face, so familiar, is always being presented under new geometry. This is why the moon can feel both constant and unstable. The pattern is dependable enough for calendars, tides, rituals, and navigation. Yet within that dependability are small variations. A full moon is not always the same size. A crescent does not always sit at the same angle. A crater near the edge is not always equally visible. A polar shadow does not receive the sun simply because the rest of the disk is bright. The moon repeats, but not as a machine repeats. It repeats as an orbit repeats, with detail inside the cycle. The surface records that same mixture. Craters preserve ancient impacts, but their shadows change hour by hour. A fault may be frozen in rock, but the moon's crust still feels tides from Earth. A cold trap may hold darkness for ages, while a ridge nearby catches sunlight again and again. A swirl may lie still on the ground, while charged particles from the sun continue to touch the dust around it. A crater floor may seem dead, while small impacts and thermal stress continue their quiet work. Everything about the moon is slower than ordinary human attention wants it to be. Its day is long, its erosion is slow, its contraction is small. Its orbital cycles stretch beyond seasons. Its surface preserves events separated by millions or billions of years. Even its apparent wobble requires patience to see. A single glance makes it seem still. Repeated looking reveals motion. That is a good way to understand the whole world. The moon is not alive like Earth. It has no forests, no weather, no oceans moving under clouds, no continents drifting across a mantle in the same restless way. But it is not a blank stone either. It is a body in relationship. Relationship with Earth. Relationship with sunlight. Relationship with impacts. Relationship with old heat, local magnetism, cold shadow, and the solar wind. It is quiet because its processes are quiet now, not because nothing remains. From Earth, the near side continues to watch over the night with its familiar dark plains. Oceanus Procellarum stretches wide and shadowed. Mare Imbrium lies in its great basin. Bright craters mark younger violence. Pale highlands hold older crust. Around the limb, features drift in and out of better view as libration changes the angle. Beyond the limb, the far side turns through sunlight and darkness without being seen from the ground. The whole moon moves together. It circles Earth while Earth circles the Sunday. It pulls on oceans while Earth pulls on its crust. It keeps old fire in frozen lava and old cold in polar traps. It carries scars from stones that no longer exist as separate bodies. It holds dust that has been broken and darkened by space. It gives the night a shape so familiar that the deeper motion can be missed, but the motion is always there. In the tides returning to shore, in the changing line of sunrise across crater rims, in the slow reveal of the lunar edge, in the hidden tremor under a fault scarp, in the long path of a body that has followed Earth for more than 4 billion years. The moon is not only the nearest world, it is the nearest reminder that stillness can be full of movement, if the watching lasts long enough. And now, the moon can be left where it has always been, moving quietly above the darkened side of Earth. Its craters remain in sunlight and shadow. Its old lava plains rest under the black sky. Its polar hollows keep their cold. Its pale swirls lie across the dust. And its broken scarps hold the memory of slow contraction. Nothing needs to be solved now. Nothing needs to be held tightly in the mind. The moon will keep its records, whether they are watched or not. Far below it, Earth turns through night. Oceans lift and lower. Coastlines breathe with the tide. Clouds drift over sleeping cities and empty fields. Somewhere, the moon is rising. Somewhere else, it is setting. Its light crosses windows, rooftops, water, mountains, and quiet rooms, softened only by the air of this planet. Arriving after a short journey through space, the nearest world remains near, but not completely known. That is enough. The surface that seemed simple has opened into rings, fractures, shadows, frozen marks, and gentle motion. Now those images can fade. The bright crater rim can soften. The long ray across the far side can become only a pale line in memory. The cold trap can sink back into darkness. The tide can turn without needing attention. There is only the slow orbit now. The moon following Earth. Earth following the Sunday. The whole system moving through a wider, dark, quiet and balanced, carrying old scars and soft light together. Let the thought of it become distant. Let the lunar ground fall away. Let the black sky widen behind it. The moon is still there, and the night is deep enough to hold it.